Imagine a universe where time itself can slow down, where space can stretch and warp, and where matter and energy are two sides of the same coin. This isn't science fiction, it's the profound reality unveiled by Albert Einstein's theory of relativity. His groundbreaking ideas fundamentally reshaped our understanding of the cosmos. Einstein's work, published in two main parts, Special Relativity in 1905 and General Relativity in 1915, challenged centuries of established physics. It moved us beyond Isaac Newton's classical mechanics, offering a more accurate description of the universe, especially at very high speeds or in strong gravitational fields. This theory isn't just an abstract concept for physicists. It has tangible implications, from the GPS in your phone to our understanding of black holes and the Big Bang. Join us as we explore the core principles of this monumental scientific achievement. Special relativity deals with the relationship between space and time for objects moving at constant speeds. It's built upon two revolutionary postulates that seem simple but have mind-bending consequences. The first postulate is the principle of relativity. It states that the laws of physics are the same for all observers in uniform motion, regardless of their constant velocity. There is no absolute frame of reference. Motion is always relative. The second postulate is the constancy of the speed of light. This asserts that the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. This was a radical departure from classical physics. These two postulates lead to astonishing effects. One is time dilation, where time passes more slowly for an object moving at high speed relative to a stationary observer. A clock on a fast-moving spaceship would tick slower than a clock on Earth. Another consequence is length contraction. Objects moving at high speeds appear to be shorter in the direction of their motion when measured by a stationary observer. The faster an object moves, the more its length contracts. Perhaps the most famous outcome of special relativity is the equation E equals mc squared. This iconic formula reveals the profound equivalence between mass and energy. A small amount of mass can be converted into an enormous amount of energy and vice versa. This principle is fundamental to understanding nuclear reactions, from the power of the sun to the operation of nuclear power plants. It showed that mass is not conserved independently of energy, but rather energy is conserved. While special relativity dealt with constant motion, Einstein soon realized it didn't account for acceleration or gravity. This led him to develop general relativity, a far more complex and elegant theory of gravity. The cornerstone of general relativity is the equivalence principle. It states that the effects of gravity are indistinguishable from the effects of acceleration. Imagine being in a windowless elevator. You couldn't tell if you were accelerating upwards or standing still on a massive planet. This insight led Einstein to a revolutionary idea: gravity is not a force pulling objects together, as Newton described. Instead, gravity is a manifestation of the curvature of spacetime caused by the presence of mass and energy. Think of spacetime as a flexible fabric. Massive objects like planets and stars create dents or curves in this fabric. Other objects like light or smaller planets follow these curves, giving the appearance of being pulled by gravity. This new understanding explained phenomena that Newton's theory could not. For instance, it accurately predicted the anomalous precession of Mercury's orbit, a long-standing puzzle in astronomy. General relativity also predicted the bending of light by massive objects known as gravitational lensing. Light from distant stars or galaxies can be deflected as it passes near massive galaxy clusters, acting like a cosmic magnifying glass. The theory also predicted the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These cosmic behemoths are now routinely observed by astronomers. More recently, general relativity predicted the existence of gravitational waves, ripples in space-time, caused by violent cosmic events like colliding black holes or neutron stars. These waves were directly detected in 2015, opening a new window to the universe. Einstein's theory of relativity has profoundly transformed our understanding of the universe. It revealed a dynamic, interconnected cosmos where space and time are not absolute but relative and intertwined. It has provided the theoretical framework for modern cosmology, helping us understand the Big Bang, the expansion of the universe, and the large-scale structure of the cosmos. It continues to be a cornerstone of fundamental physics. Beyond its theoretical elegance, relativity has practical applications. The precise timing required for GPS satellites to function correctly relies on accounting for both special and general relativistic effects on time. Without these corrections, your GPS would be inaccurate by miles. Einstein's theories inspire us to question assumptions and to look beyond the obvious. They remind us that the universe is far more intricate and fascinating than we can often imagine. The journey into relativity is a journey into the very fabric of existence. It challenges our intuition, but ultimately rewards us with a deeper, more beautiful understanding of the cosmos we inhabit.